So this is exercise 1 from chapter 1 of Atiyah's and Macdonald's Introduction to Commutative Algebra. So the exercise is that we have to prove that the sum of a unit and a nilpotent is itself a union. So before we do the exercise, we have to make use of two facts. Namely, one, that the nil radical of the ring is the intersection of all its prime ideals. And the second fact is that every maximal ideal is prime. First one is pretty easy to see. If we have a nilpotent element, then some power of it is 0. But 0 is contained within a prime ideal. That automatically means that the nilpotent itself is also contained within the prime ideal. Second one is also pretty easy to see. It follows directly from the fact that a field is an integral domain. So now let's do the exercise. So let U be a unit and let N denote a nilpotent. So what we're going to do is we're going to do a proof by contradiction. Namely, we're going to suppose that U plus N, the sum of the unit and the nilpotent, is not a unit, so it's a non-unit. But what we can then see is that the ideal generated by it is not the entire ring. Because if it would be the entire ring, then it would generate 1, which is characteristic of a unit, and not a non-unit. So it's not the entire ring. And what this means is that either it is the maximal ideal, a maximal ideal, or it is contained within the maximal ideal. So that N denotes the maximal ideal. So U plus N generates an ideal that is contained within a maximal ideal. Now we're going to invoke the second fact, namely every maximal ideal is prime. So we also know that the ideal generated by U plus N is contained within some prime ideal. Now what this means is we invoke 1, namely every nilpotent element is contained within every prime ideal. So what we can say is, okay, N here, no matter what our prime ideal is, it's going to be contained within it. And since ideals are abelian groups, we can say, okay, let's take this U plus N element and subtract N. Since they're closed under addition, that means that the resulting element, U, must also be an element of this prime ideal. However, U is a unit, and it's absurd to have a unit within the ideal, because that would generate the entire ring. So we've arrived at a contradiction, which means U plus N is in fact a unit. So there's another way to prove this. This is how I did it the first time, and it's to algorithmically show what the inverse is. You could do it as an exercise, but this is a way nicer proof for that.